Good morning, good evening, everyone. This is Vishal Baskar presenting for DVCon 2023, and the topic for the day is do not forget to cover your SystemC code with UVMC. For decades, it is known that SystemC is used for modeling high levels of abstraction, which can be used with system Verilog components. One of its greatest strengths is the versatility in mixed language designs, offering various mechanisms and constructs required for embedded systems modeling. But when it comes to verification of those SystemC models, it is important to verify them at any level of abstraction. SystemC is fast becoming a standard and is widely being adopted by the industry for system-level modeling, undoubtedly. Hence, it makes sense that the verification is extensively performed. Further investigation and research are needed to ensure the IEEE 1647E functional coverage language features are supported in developing such libraries that would eventually become a standard in the future. So now let's look at a viable solution that we have created here to utilize functional coverage usage by exporting them from SystemC to System Verilog each time a sampling event is called on the SystemC side. Going over the basics, a coverage model includes one or more cover groups which represent a dataset to be sampled under certain conditions, typically with a sampling event. The approach would be to send packets of data from SystemC side to the System Verilog side, which can be used for sampling functional coverage each time the sampling event is triggered. The diagram described here shows how the packets are sent from SystemC side to the System Verilog side while the sampling event is triggered in the SystemC side. We have described two examples in this paper, where one would deal with utilizing transaction level modeling sockets and generic payloads, and the other with transaction packets made from template specialization class. In first example, we have a producer UVM class, which is from our generic SystemC producer. We pack that class that connects to the System Verilog side by using a simple initiator socket, and then send a generic payload in the form of a transaction using TLM 2.0. There is a simple System Verilog consumer TLM model that prints received transactions of type UVM TLM generic payload. The class is derived from UVM sequence item, which enables it to be generated in sequences and transported to drivers through sequencers. In the snapshot, you can see that out B transport is being sampled and is called here in the System Verilog side. You can also see that we declare a cover group System Verilog header and observe the values of the types passed, like command and data from the SystemC side. In the second example, instead of a generic payload like we just saw, we send transaction in the form of packets. Here, we have used a transaction class where we need not have the same declaration number, type, and order in both SystemC and System Verilog. We can utilize a converter class, which means the transaction definitions are allowed to be completely different. In our case, since we utilize the converter classes doPack and doUnpack method, one would stream members of the transaction to and from the packer variable. The producer class contains the input transactions which are packed and sends it to the System Verilog side. The producer sends TLM transactions in the form of blocking transport to System Verilog every time. We have a consumer class that extends from packet base. This is where we would apply coverage to the transaction received from the SystemC side. A blocking transport function is responsible for establishing a connection on the System Verilog side and unpacking the data. A sampling event is triggered each time the blocking transport from the SystemC side sends a TLM transaction and on the system Verilog side, the coverage function is sampled. For this approach, we attempted the use of TLM sockets and ports present in examples 1 and 2 respectively. In example 1, we utilized UVM generic payload transaction class, which had data members like address, data, command, etc. Once we were able to identify the width and the bins to cover, we were able to see good results. In the second example, we used a template class to send packets containing addresses and data to the system Verilog side from the SystemC side. We were able to capitalize on the do-pack and do-unpack methods of UVM, and the coverage results show that all bins in the cover point were covered. In this paper, we discussed existing methods for performing functional coverage directly on SystemC models, but none of them are industry standard libraries. Currently, we do not have an industry-wide solution to perform functional coverage on SystemC models. Rather than having a class-based transaction passed as an object to a cover group, utilizing constraint randomization and assertions on TLM generic payloads directly would certainly be more helpful. It would also help improve the overall coverage goal and identify holes in coverage space. This can also be scaled up to signal processing models that are designed in SystemC. It would be helpful to identify how various signals that are sent in are sampled and verified using coverage, constraint randomization, etc. Thank you.